The exhaust gas temperature gauge and the cylinder head temperature gauge are often confused with each other. However, they do perform different functions. The exhaust gas temperature probe is installed about 4 inches from the cylinder head on the exhaust system. Although the exhaust gas temperature gauge can help in troubleshooting a problem on the engine, it's primarily a fuel management instrument. On the other hand, the cylinder head temperature gauge is an engine instrument designed to protect the engine against its enemy, excessive heat. Most general aviation aircraft engines take the cylinder head temperature off the hottest single cylinder of the 4, 6 or 8 cylinders. The hottest cylinder is determined by extensive flight tests carried out by the engine manufacturers. Minimum in-flight cylinder head temperature should be about 150 degrees Fahrenheit, and maximum in most direct drive normally aspirated engines is 500 degrees Fahrenheit. Some of the higher powered, more complex engines have a maximum limit of 475 degrees Fahrenheit. Although these figures are minimum and maximum limits, the pilot should operate his engine at more reasonable temperatures in order to enable it to achieve its expected overall life. In practice, it's been found that engines have benefited greatly during continuous operation by keeping cylinder head temperatures below 400 degrees Fahrenheit in order to achieve the best life and wear. In general, it would be normal during all-year operations in climb and cruise to control the cylinder head temperatures in the range of 350 degrees to 440 degrees Fahrenheit. The way the mixture control works has been described previously in the carburation lesson. We'll now describe its operation during the takeoff and landing phase, the climb and cruise, and also its use as an idle cutoff. We know from the carburation lesson that detonation is most likely to occur under conditions of high charge temperatures and pressures. The takeoff phase of a flight is exactly when these conditions will occur, and also, as it could be likely that we may have to go around from the landing phase, once again generating the same conditions as on takeoff, we must select a fully rich mixture in both circumstances. The addition of extra fuel into the cylinders reduces the volumetric efficiency of the engine, which somewhat reduces the potential of the engine to produce power, but, on the other hand, the cooling effect that the evaporation of the fuel has on the charge prevents detonation and therefore allows the engine to deliver its maximum rated output. We also found from the carburation lesson that because of the air's decreasing density with increasing altitude, our mixture gets richer as the aircraft climbs, because the weight of fuel being fed into the cylinders doesn't reduce by the same proportion. As long as the climb doesn't continue above, say, 5,000 feet, this isn't really a problem. The rich mixture does the same job it did during the takeoff phase. It stops detonation by cooling the charge temperature, so the mixture control can be left at fully rich. During the cruise phase of flight, the mixture can be leaned off to give better fuel economy. If your aircraft has an exhaust gas temperature gauge, then this can be used to give an indication of the correct mixture setting. If the mixture control is moved towards lean, the temperature will peak at the ratio of 15 to 1. It should be remembered that this ratio must not be used, as detonation will occur. On reaching the peak exhaust gas temperature, the mixture control should then be moved towards rich, and the cylinder head temperature will drop. The aircraft's flight manual will specify a temperature drop, which will give the rich cruise setting. If an exhaust gas temperature gauge is not available, then this alternative method of setting the correct mixture strength for the cruise may be utilized. Moving the mixture control from fully rich to a weaker setting brings the air-fuel ratio closer to the chemically correct value of approximately 15 to 1. Remember, at this ratio all of the air and fuel are consumed, and the heat released by combustion is at its maximum. More heat means more power, so with a fixed pitch propeller the RPM will rise, and airspeed will increase as more power is produced. Weakening the mixture from this point will make the RPM drop. Pushing the mixture control back towards rich, to where the chemically correct mixture was found, will bring the engine speed back up, but this cannot be maintained without risking the generation of detonation. To prevent this happening, the mixture control should be moved back to a position richer than that where the peak RPM was found. When the RPM will at first rise as it passes through the 15:1 setting, and then fall slightly, this position can be assumed to be the optimum for a rich cruise. The normal method of shutting down an aircraft engine is by cutting off the fuel supply. This has several advantages over the method used in automobile engines, where the ignition is switched off instead. Cutting off the fuel ensures that the engine cannot run on, a phenomenon which can occur if the engine has any incandescent carbon deposits in the combustion chamber. It also means that no fuel is allowed to be sucked into the cylinders during those last few revolutions before the engine stops. Any fuel brought into the cylinder after combustion ceases will tend to wash the lubricating oil from the cylinder walls, and as a consequence, the next time it starts, the engine suffers a tremendous amount of wear. In the carburation lesson, the idle cut-off section of the carburetor was described in some detail. The idle cut-off may be a separate control, or it may be incorporated into the mixture control lever. By pulling the mixture control lever to the ICO position, the fuel flow between the float chamber and the venturi is cut off.